Dear students, in this video, now we are going to discuss the spectroscopic terms and notations. As we know that the individual orbital angular momentum states can be described by a small letters or lowercase letters, which correspond to the different value of orbital angular momentum quantum number. So which correspond to the capital letter and which describe the entire electronic state of an atom according to its total orbital angular momentum. We can describe the electronic state of an atom by using the quantum numbers like n, which is called as the principal quantum number, that is the principal quantum number, and using the L, which is called as the orbital quantum number, and in the similar way S, which represent the spin quantum number, and we have the J, which represents the total angular momentum quantum number. Total angular momentum quantum number. Okay, so we have the scheme of quantum numbers which describe the electronic state of an atoms. For example, we have the n for n is equal to 1, that is and you know that represents the principal quantum number, that is the shell within an atom. It represents the different shell. For n is equal to 1, then L, which represents the orbital quantum number which describes the subshells. So for n is equal to 1, L has the value, it can have the value 0. Okay, and then this corresponds to the L is equal to 0, it corresponds to the S subshell. For n is equal to 2, L can have the values 0 and 1, and it corresponds to the S and P subshell. And similarly, if the value of n is the 3, then value of orbital quantum number will be equal to 0, 1 and 2, and correspondingly L is equal to 0 correspond to the S subshell. For L is equal to 1, we have the P subshell, and for L is equal to 2, we have the D subshells. So we can write that there are the different subshells, there are the different electronic states which correspond to the individual orbital angular quantum numbers, that is for L is equal to 0, 1, 2, 3, 4 up to so on. We have correspondingly, we have for L is equal to 0, there is the S state, P state, and there is the D subshell and F subshell and so on, G. So there are the different electronic state, or there are different subshells which correspond to the different value of orbital angular momentum quantum number. We represent these states with the lowercase letters S, P, D and F. Now here we are going to discuss the similar schemes to describe to designate the entire electronic state of an atom according to its total orbital angular momentum, and it can be represented by the capital letters. Now here we will discuss the similar scheme to represent the total represents the entire electronic state of an atom according to the total orbital angular momentum quantum number, which can be represented by the capital L, and is equals to 0, 1, 2, 3, and so on. So it can have the different value, and corresponding state can be represented by the capital letters. For L is equal to 0, we have the S state. For L is equal to 1, the correspondingly we have the P, and for L is equal to 2, we have D and F up to so on. So these are called as the spectroscopic tones, or spectroscopic, or also called as the term samples. So now we go to another important thing, which is called as the multiplicity. As the subscript, there is the superscript before the sample. For example, if we have the term sample P and there is the letter, for example, 2, here the 2 is called as the multiplicity. It represents the multiplicity, and it indicates the multiplicity of states, that is, which is the number of different possible orientation of L. It represents the different possible orientation of L. Orientation of L, that is how many orientation of L are possible, or how many values or different values of L are possible, and it can be represented by superscripts before the term samples. So there are the different possibilities for the of the multiplicity. For example, here we have the different possible values. We have the different orientation of L, so we have the different possible value of total angular momentum J. So for example, it has the value of it can have the value of 2s plus 1. Its multiplicity will be equals to the 2s plus 1 when L is greater than S. That is, we can say that the J can has the value from of a range of the value from J equals to L plus S through 0 to L minus S. So for example, if S is equal to 0, the J will be equals to 1, which correspond to the singlet state. That is correspond to the singlet state. And uh, so uh, let's suppose if S is equal to 1 by 2. If S is equal to 1 by 2, then J will be equals to the 2, that correspond to the doublet state. So there will be the two possible value of the J for S is equal to 1 by 2, that is multiplicity will be the 2, and for S is equal to 0, its multiplicity is 1, and we get the singlet state. And so J can have also J can have the value J is equals to when L is equal to for example when S is equal to 0, S is equal to 1, then when S is equal to 1, we have the triplet state. Its multiplicity will be equals to the 3. We have the triplet state, and value of, in this case, the J value of the J varies from L plus 1 to L and through L minus 1. So in configuration, in the situation, let's suppose we have another situation in the case like when S is greater than L. If we have such a situation, then multiplicity instead of 2s plus 1, it will be equals to the 2l plus 1. So the total angular momentum quantum number used as a subscript. For example, in this is the term sample, and this one is the multiplicity. It can be equals to either 2s plus 1, or either it can be the 2l plus 1. Depends on the situation, either s is greater than l or or l is greater than s. So it's here this one is the term sample which correspond to the different value of l. 2s plus 1 is the multiplicity, and subscript j, here the j which is the total angular momentum quantum number, and it's used as a subscript. For example, let's suppose the value of the j varies from j, it can have the value of l plus 1 by 2, or it can have the j can have the value of l minus 1 by 2, as s is equal to half l plus minus s. So it can have the value of l plus 1 by 2, or it can have the value of l minus 1 by 2. So let's suppose if l is equal to 0, then the possible value of j will be equals to the j and the value of plus half, or it can have the minus half values. And j is equal to 1 by 2 is not allowed, and the negative value of angular momentum quantum number is not allowed. So there is only one value of the j which correspond to the j is equals to plus 1 by 2. Although the multiplicity will remain the same, that is j is equals to multiplicity is equal to j is equal to 2s plus 1, and so 2 into 1 plus 1 by 2 plus 1, and it will be equals to the 2. Although we ignores the negative value, but still multiplicity of this will be equals to 1 by 2. So how we can write the spectroscopic notation for L is equal to 0. So the spectroscopic notation for L is equal to 0, that is, you know, that L is equal to 0, 1, 2 up to so on. Then correspondingly we have S, P, D and different states. For L is equal to 0, we have the spectroscopic term S, multiplicity is 2s plus 1 which is equals to the 2, and j has the value of 1 by 2. So this represents the spectroscopic term samples for L is equal to 0. And let's try another value of L. Let's suppose L is equal to 1. Then the spectroscopic term sample correspond to L is equals to P. Now what are the possible value of the j, and first are the spectroscopic notations. For j, you know that j is equal to L plus 1 by 2, or either it can be equals to j is equal to L minus 1 by 2. For j is equal to L plus 1 by 2, for L is equal to 1, we have either L is equal to 1 plus 1 by 2 or 1 minus 1 by 2. So corresponding value of the j are 3 by 2, or either it can be the 1 by 2. So again the multiplicity 2s plus 1, and it will be equal to 2 into 1 by 2 plus 1 is equal to 2. So multiplicity is the 2, and we have here we have the two terms, that is equals to 3 by 2, and the second term will be equals to the term sample for L is equal to 1. Again it will be equals to the P, and we have the 1 by 2 and multiplicity 2. So there are the two spectroscopic terms which correspond to L is equal to 1, and so multiplicity uh, of the state is total angular momentum is 2. So there are the two corresponding spectroscopic terms are two spectroscopic states, total angular momentum or electron states, which are 2p 3 by 2 and 2p 1 by 2. So now we can summarize the whole situations of term and samples of spectroscopic notations. And let's suppose we have the S, it represents the state, and then we have the orbital angular momentum L, and then we have the total angular momentum J, and we have the spectroscopic notation. So for state for S we have the L is equal to 0, and so the possible for L is equal to 0, J has only one possible value, J is equal to 1 by 2, and spectroscopic notation will be equal to the 2 1 by 2, it has the multiplicity 2 and this one. And for P state, for P value of L or it will be equals to, it correspond to P is equal to correspond to L is equal to 1, and for L is equal to 1 we have the two possible value of the J, and correspondingly spectroscopic notations will be 2 3 by 2 and P 2 1 by 2, and similarly D state will correspond to L is equal to 2, and for this one we have again two possible value 5 by 2 and 3 by 2. It corresponds to the D 2 5 by 2 and D 2 1 by 2. So there for D is equal to 2, which correspond to L is equal to 2. Again we have the two spectroscopic terms. Now we can explain it with the help of an example, and let's suppose the term sample for the sodium ground state, it can be represented by 3s2 1 by 2, and its first excited state term sample is equals to 3 2 and then 1 by 2, as 3 here represents the principal quantum number. So sometime we before the term sample we use this principal quantum number which represents the shell of an atom. So the term sample for the sodium, and this one is the first sodium ground state, and this is for the first excited state is 3p1 by 2. Now we need to list the possible quantum number n, l, j and mj of outer electron in each case, of outer electrons in each case. So first we will take the case of ground state 3s2 1 by 2. So for this case you know that n will be equals to the 3. So here 3 represents the principal quantum number. For n is equal to 3, L, as we have the s state, so L will be equals to the 0, and J for L is equal to 0, you know that J has only one possible value, J is equal to 1 by 2. J has the multiplicity of 2s plus 1. So for L is equal to 0, J is equal to L plus s, and its multiplicity is 2s plus 1. So it has multiplicity is the 2, although multiplicity is 2, but it has on for s L is equal to 0, it has only one possible value, J is equal to 1 by 2. So now the possible value of mj, as mj you know that it represents the possible orientation of total angular momentum quantum number, and it varies from minus j to plus j. So for j is equal to 1 by 2, mj will be equals to the plus minus 1 by 2. Okay, now we comes to the first excited state. For first excited state 3 p 2 into 1 by 2, as again n will be equals to the 3, as p represent L is equal to 1. For L is equal to 1, the possible value of the j, or either it can be the 3 by 2 or it can be either 1 by 2. So for j is equal to 3 by 2, j is equal to 3 by 2, the multiplicity for j is equal to 3 by 2. The possible value of mj, it will be equals to the uh, minus 3 by 2, minus 1 by 2, plus 1 by 2, and plus 3 by 2. So possible value of mj are, there are 4 possible value of quantum number mj correspond to the j is equal to 3 by 2. Now for j is equal to 1 by 2, the possible value of mj will be equals to the, either it can be plus 1 by 2 or minus 1 by 2. So for j is equal to 1 by 2, the possible orientation of total magnetic quantum number are either plus 1 by 2 or it can be either minus 1 by 2. So this was all about the spectroscopic terms and notations. Thanks for watching. For more videos, please subscribe our channel.